there was a factor missing. So originally, wait. Oh, I can't hear you. Just a minute. Yes, someone said something. Hello.
No, ma'am, that was the meeting is starting recorded like that.
Okay. Okay, thank you. So there should have been a factor of half over here. So does that solve your confusion, Doipayan, or is it something else?
Yes, ma'am. Yeah, that was one of the problem because I didn't get where does the two factor goes,
Yeah.
and
So that
and the
originally there was
second
half.
second one is that you have written that it is not an exchange integral.
This
So
one, yeah. So the one that I have written over here, this is not an exchange integral because see, B and B bar are different spin orbitals, and
in
A and
that
A
case,
bar are.
we have the same argument in Coulomb integral also.
No, so all Coulomb integrals look like this, right? And we have not taken anything which is A bar or B bar.
Initially, we wrote the terms, but we saw that these terms will go to 0 and the remaining terms will be 4.
Okay, so here actually, okay, yeah. So this is not a proper Coulomb integral. That's true. Maybe we should not have written it in the full expression. So this was the class even before that. Right? So this is lecture 9. This is, yeah. So here we wrote at the end. Yeah, so this one. Yeah, so these are also not actually. So these are also not Coulomb integrals. But we didn't make a mistake because they were anyhow 0. This is beta, this is alpha, and this
Yes,
is again beta.
final terms will be same, but initial the terms that you have taken,
Yeah,
I am confusing
this,
with that.
yeah, okay, my mistake. You are absolutely right.
Okay, ma'am.
These are also not Coulomb integrals. So, did everyone else get the point also?
Sangita.
Yeah.
Sangita. Yeah. I just thought, physically they should understand between Coulomb and exchange integral. Why for Coulomb 4 comes and why for exchange twice come? Because in Coulomb, the electron 1 is on one particular orbital, spin orbital. Electron 2 is another spin orbital. So it has chi A star 1, chi A 1, chi B star 2, chi B 2. So the spin orbitals can be independently alpha and beta. So there are 4 possibilities. Whereas in the exchange, chi A star 1 and there it is chi B 2. Chi A star 1 and there it is chi B 1. So either A and B both have to be alpha or they have to be beta. So only there are 2 possibilities. So I think physically you can understand why it is half into 4 and half into 2. Mathematics
Because only same spins can exchange. So
yeah, only same spin can exchange. Yeah. Both A and B have to be same spin orbital. You think in terms of spin orbitals and think of the possibilities. For the Coulomb, the spin orbital for 1 and 2 are independent. So both can be independently alpha or beta. So that is what the mathematics is reflecting. See, mathematics is nothing but reflection of this physics. Okay. So, I mean, if these two are understood hand in hand, then it will become easier, I think. Okay. And of course, mathematics is explaining whatever I'm telling in physics. So that is why certain integrals in exchange are dropping out. Because it is alpha, beta, spin, or the orthonormality. And then you write everything in terms of space orbitals. So what you are seeing as 2 times this minus 1 times this is just in terms of space orbitals. After the integration, what survives? After the spin is integrated. Okay, anyway, I think you continue. Sorry.
Yes, yeah. Thank you. No,
okay.
Thank you.
Yeah.
Thank you.
Okay.
Okay. So this was one part. Okay, and also from the lecture 10, I corrected a part of the Coulomb and exchange operator. So I will go through that in case you have not looked at it. So in the notes that was uploaded, this part I have written out nicely now. So the point is, so how do you get Coulomb and exchange operators, and what do they mean, the operators? Okay. So what we want is that the Coulomb integral and the exchange integral, they look like some sort of expectation value of an operator. So we want JAB to look like an expectation value of some operator JB with respect to chi A, and then we want to find out the form of JB. So that is simple. You write out the full integral, then you take out the integration over chi A star 1, so over the coordinates of electron 1, and the remaining you define as the operator JB1. Okay, so the operator acting on chi A1 is JB1, and then whatever is left after you remove chi A star 1, which is part of the bra, and chi A1, which is part of the ket, and the integration over dx1 is the operator acting on chi A1. Fine. Now for the exchange, you need a little bit of more tricks. So if you simply write out the exchange integral like here, then you see we have a chi A star 1, but we have a chi A 2. Okay. So even if I say that my KB operator is acting on chi A 1, my right hand side will end up with a chi B1. If I just take out all the terms that depend on the coordinates of electron 1. So then what is the trick? The trick is you introduce a permutation operator which permutes the coordinates of electron 1 and 2, and you insert it before the unstarred spin orbitals. Then you see, so what did I have? I had chi B1, chi A2. So I can write that as a permutation operator acting on chi B2, and chi A1. So when it gets permuted, you get back the original integral. And once you do that, then you can take out chi A1 on the right, and you end up with an operator form, and you have the same function on the left and right hand side. So you can either use this expression or you can use this expression. But to maintain an analogy with the Coulomb operator, the second one is analogous to the Coulomb form. So if you want the same function and you want to, let's say, remove the function for some reason and write only the operator, then you have to take the second form. Okay. And then when we took the variation of the Lagrangian, then you see that we wanted to take out the function, the same function, and get one common operator with j minus k in it. So that's why we have used the, so here the form that is implied is the one with the permutation operator. Okay. So if you remember last class, I hope this is now clear. Does anyone have any more questions? I think last class I didn't do a good job with the operators, so I repeated it now. Yeah. It's okay. Does anyone have any questions from last class? Because last class we did something that was quite new to you, I think. No? Okay, then I will just go through it quickly once, just to revise in case you have forgotten, because we will continue from there. So we wanted to derive the Hartree-Fock equations. So our goal was to reduce, to get an equation which determines the spin orbitals. And the condition for determining the spin orbitals was the variational theorem. And since the Euler theorem, which tells you that a variationally optimized wave function is a solution to the Schrodinger equation, since that is just an existence theorem and you cannot obtain the exact wave function because you cannot have an infinite space in which to expand the wave function and then carry out a global minimization. So the way that you proceed is that you take a guess for the form of the wave function, which in the Hartree-Fock case is a single determinant containing spin orbitals, and you apply the variational principle to obtain the spin orbitals. Okay, in a restricted space. So this is a restricted variation. So that is what we wanted to do. We wrote the wave function as a determinant. Then we wrote a Lagrangian to introduce the constraint that the spin orbitals should remain orthonormal when we vary them little by little. So when we go from chi A to chi A plus delta chi A or chi B to chi B plus delta chi B. So variations should be such that the set remains orthonormal. And this was introduced in the Lagrangian with a prefactor, which was the Lagrange's undetermined multiplier. We found that it should have the dimensions of energy because the Lagrangian has the dimensions of energy and the overlaps are dimensionless. We also found that the Lagrangian multipliers, they can be placed in a matrix which is Hermitian. Then we set the variation in the Lagrangian to 0, which is the variational condition. And we obtained the various terms that arise from this variation. So since the energy, which is the first term in the Lagrangian, that has the 1 electron and the 2 electron integrals, which we obtain all the explicit terms that arise from the variation of the spin orbitals. Then we also did the 2 electron terms, okay? And then we defined the exchange operators to make it more concise, the Lagrangian, and we ended up with an equation for the spin orbitals, okay? But this is, but like we noted then, that this does not have any particular form. This is an equation definitely, and it can be used to determine the spin orbitals, but it is not easily solvable. What we know is that the Hartree-Fock equations are actually some sort of an eigenvalue equation. I guess you have heard of this, and it goes through some sort of diagonalization procedure in a way, but this does not look like an eigenvalue equation. So that is because here the epsilon matrix that is involved in this equation is not diagonal. So you see, if epsilon was diagonal, then this equation could be reduced to a set of eigenvalue equations, right? So if epsilon BA was just epsilon BB, let's say, or yeah, epsilon BB, then you would have you can separate them out into n eigenvalue equations. So that is what we want to do. We want to somehow reduce this to an eigenvalue equation, and we will do that today. Okay. So let's start on that. So, and this eigenvalue form of the Hartree-Fock equation is called the canonical Hartree-Fock equation. So let me start with by repeating the final form. So this is what we had obtained before. And the Fock operator. Yes.
Yeah, I just you are deriving canonical equation now.
Yes.
Yeah, okay. The equation that you have written is not canonical. It is a
No, this is not canonical.
Yeah, yeah. So because you headline canonical, so I was confused. Okay, fine.
No,
Yeah.
I'm deriving it now.
Yeah,
I
yeah.
haven't.
Fine. I understood. Okay.
Yeah.
Sorry.
So the Fock operator, let's say for electron 1, that is the one electron part and the Coulomb and exchange operators that we defined before. Okay. So let's see. So we have a set of spin orbitals chi a, and we want to go over to another set of spin orbitals chi a prime, and chi a prime should be such that epsilon matrix is diagonal. This is our goal. So what do we do? So we say that we have a new spin orbital which is obtained from the set of old spin orbitals by a unitary transformation. So this is called a unitary transformation. So what does that mean is that you multiply with a matrix which has the following property, that is U dagger is equal to U inverse. This is the condition for a unitary matrix. Okay, and what is dagger? We will need this, so let's recall. So U dagger is equal to U star transpose. Okay. Then next. So our determinant of spin orbitals looked like this. Sorry. Chi 1 1, chi 2 1, etc. and chi n1. Okay, so it looked like this, and corresponding to this determinant, we consider a matrix A, which is the same determinant in matrix form. So chi 1 1, chi 2 1, chi n1, then chi 1 2, chi 1 n, chi n. So this is a matrix corresponding to the determinant. So the wave function psi naught is determinant of the matrix A. Okay, and the normalization factor is also there, so 1 by root n. Right. Now let's see what happens to this matrix when we apply the unitary matrix and we have a corresponding matrix of the new spin orbitals as well, which we call A prime, which comes from the set chi A prime. So to obtain this matrix, we can apply the unitary matrix transformation, which we were applying element wise to every spin orbital. The same thing we can do to the full matrix. Okay, and if you open it out and see, then this is again, so okay, is it necessary for me to write it out? Okay, I'll write it out anyway. So this looked like this. And U looks like U11, U12, U1N, U21. Okay. If I multiply this, then every element becomes the new spin orbital. So to obtain the first element, we're multiplying chi11 with all the with this full column, right? So I'm multiplying this with this. So this is the same as the expression for the individual spin orbital, which was summed over the first element of the unitary matrix. So that's B. So there's the sum over B in this expression. So we get a new matrix, which is basically chi1 prime 1, chi1 prime n, chi n prime 1, chi n prime n. So then definitely we can call it A prime. And my new wave function, psi 0 prime, is then 1 by root n, determinant of A prime. Okay, no problem with this, right? Simple enough. Also, what is determinant of A prime? So A prime is equal to AU. So determinant A prime is equal to determinant A into determinant U. And determinant U is
Ma'am,
equal to
isn't
1.
that n factorial?
Sorry, yes. Yes. Thank you. Not paying attention. Fine. And so determinant of A prime is equal to determinant of A into determinant of U. Okay. This is a mathematical property. And determinant of U is 1. So this is the first exercise for today. Show that determinant U is equal to 1. You know the property. So I mentioned the property of the unitary matrix, that U dagger is equal to U inverse. Can you all try to show this? So I'll give you 5 minutes, okay? And after that, if someone can do it, very good. Otherwise, I'll work it out. So I can give you a hint of where to start if you like. So since U dagger is equal to U inverse, then U dagger is equal to 1. Or unit matrix.
Madam, complete.
Yeah, you got it? Okay.
Uh,
So can you tell me?
Madam, U and U inverse equal to I. So both side determinant. So determinant I equal to 1, and determinant U and U dagger, that is determinant U into determinant U dagger.
Yeah. Yeah. So it's simple. Okay. Everyone understood? You just have to open it out. So you just do, let's say you start with U dagger equal to 1. U dagger U equal to 1. You take a determinant. Determinant 1. So this is 1. So this is basically determinant of U and star, just the complex conjugate of the value of the determinant U. Then you have determinant U is equal to 1. So this is mod determinant U square equal to 1, which means determinant U equal to 1. Okay. Clear? Okay. Now, yeah.
Sangita, just wanted to mention that in general, the determinant U will be a phase factor. It can be 1, but in general, it will be an exponential I theta kind of thing. Because
Yeah, I mean,
U
I
star.
wanted to say that from this you can guess that it will always be.
Well, what I'm saying is that it need not be 1. It can be a phase factor, exponential I theta, and that does not.
Yeah, because this is a mod square. Yes. So actually, I would have mentioned it like 1 minute afterwards.
So since you wrote equal to 1, I mean, equal to 1 is a solution, but the more general solution is a phase factor. And then your wave function will also change by a phase factor, which is absolutely fine.
Yes. In general, if you see, so since this is the mod square equal to 1, you can also have determinant U equal to e to the power I theta in general. And then also, that also implies that modulus of determinant U square is equal to 1. Okay. So this means that my psi 0 prime and psi 0, they are related by a phase factor. In a way. Yeah. So we had this, right? We had this. So from that, we can say that the two wave functions that we get by changing the spin orbitals by means of a unitary transformation give me wave functions which only differ in a phase, which means that any expectation value will remain unchanged. So by using a unitary transformation on my spin orbitals, I don't change the physical content of the wave function. That is why we have used a unitary transformation. If we had said any transformation, so you see, so when we started here, so this is sort of wise after the event. So why did we choose a unitary transformation? So the justification is that if you have a unitary transformation, then we ensure that the changed wave function is only related by a phase. So we are not changing the wave function in any way. If we chose a general transformation, we could have obtained an entirely different wave function, which of course we don't want. We want the variationally optimized wave function. We only want our epsilon matrix to be diagonal. Okay. We are trying to get to a particular set of spin orbitals, which will be one particular solution. So basically, our variational principle tells us that we can have many different solutions of spin orbitals. But just to get a more physical idea, where every spin orbital is associated with only one energy of some kind, we want our epsilon to be diagonal. Okay, so now we have got an idea that the transformation should be unitary. But what should the transformation be? We still haven't obtained the form of the transformation. So let's start with that. So we have to first see what would happen if we transformed the Fock operator. So the operator that we defined here, containing the 1 electron and the 2 electron parts, this is called the Fock operator. Okay. And now we want to first see, since the Schrodinger equation will have not only the wave function but also the Fock operator, we also want to see what happens to my Fock operator when I transform it. So the Fock operator has how should I write it? So there is a 1 electron part, okay, where you have which in the operator you don't have any orbitals, right? In the 1 electron part of the Fock orbitals of the Fock operator, so that doesn't change. Then you have the JB sum B operator. This, remember, contains some integrals, so this will change. And you have sum B KB prime, so the exchange part also contains some orbitals, so this will also change. So then we start with the first one. Let's see what happens to the Coulomb operator. And these are now new orbitals. So we write them explicitly. Let's say sum over C. Now there was a star here. So this is U C B star. Then you have R12 inverse, and that is now, let's say, D. Sum over D, chi B2 UDB. Okay. Then we take these two out and then sum them over B. So you have sum CD, sum B U star CB UDB. Okay. And this is okay. Write it out explicitly. This is the BC element of U dagger. And this is my old Coulomb operator, right? CD, and this is now delta CD, because this is a unitary matrix. Delta C. Sorry, what did I do? I made a mistake somewhere. Let's see. So there was this, there's B. Aha, sorry. Not careful, not careful, not careful, not careful. They are all C's. C, 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 C. So this is JC. So this is sum then D, J, D. Okay. Did you follow? Did you follow this? Okay. So then, what have we obtained? So we see that the Coulomb operator as a whole, so the sum that is present in the Fock operator is invariant under unitary transformation of the orbitals. Okay, so individual elements are not invariant, but the total sum remains the same. So then there is no problem. Similarly, we can show the exchange. Now, since we have a long class, you can try to do the exchange. So take the summed exchange operator and repeat the procedure that we did for the Coulomb integral. And you should also obtain that the exchange operator, the full exchange operator with the sum, that is invariant under unitary transformation of the orbitals. You just have to open it out and do what we did before. Okay. So I'll again give you 5 minutes. And you will be done in 2, I hope.
Ma'am, in the Coulomb integral,
Yes.
You have replaced the prime spin orbitals with the non-prime spin orbitals and the unitary operator, I think.
Yes.
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 So in the second one, it means chi b prime 2, you should have written chi c 2 UCB in the last part.
No. In fact, I should have written chi b prime u d. I mean, my chi should have been d. Because I've written 2 sums. Yeah.
Then the integration of the Coulomb integral will be chi c 2 chi d to R1 to inverse.
Yeah. This will be.
Is this a Coulomb integral? Because the spin orbitals have exchange. Yeah, spin orbitals are not same.
1 minute. Sum chi c d.
Excellent. Sangita,
No, 1 minute.
What is the confusion?
The confusion is with this transformation. Since I've written the 2 orbitals separately, then when I have this integral where there is chi c R1 to inverse chi d, they're saying that is not a Coulomb integral at all, but
it doesn't matter. It doesn't have to be Coulomb integral. No, so you are just showing that the unitary transformation does not change the operator.
Yes, exactly. So
okay. I understand.
I'm just showing that it doesn't change, but 1 minute. That is delta C.
Yeah, but there is a delta condition on CD.
Yeah, there is a delta condition on.
Actually, ma'am, you have written the delta condition later.
Yeah. So I think it is very clear.
Yes.
So afterwards,
Yeah.
Okay.
Yes, it is fine.
I should not have just written it over here. I should have let it be like the integral.
The integral itself, and then assume the delta condition.
And then it becomes J.
Yeah. Okay. Fine. Thank you.
Yeah. In trying to avoid writing too much, I went wrong. So You have to keep repeating the integral till I get here. Yeah. So that is the confusion. Is the exchange integral turning out fine? The exchange operator? So everyone got it right? It's exactly the same as the Coulomb integral. Now I've even worked it out, so you can see if you manage to do the same thing. Is there anyone who is stuck? I can't see your faces, so you have to speak up.
Madam,
Yeah.
in the both cases, the delta part, is it coming from the unitary matrix, that summation, or the integral? I mean, I didn't understand that part.
It is coming from the unitary matrix.
Oh, okay,
So since
so
U dagger U is equal to a unit matrix, then the condition on the elements is that every element. Let's see. U dagger. Let's say U. So I'm summing on C. So B C. That is equal to delta A B. So U A B. So U dagger U A B. I will not. U dagger A B element. That must be delta A B. And if you look at the matrix multiplication form, then it looks like this. Or
It should be U dagger. No, if you
U
write
dagger.
like this, it should be U dagger AC,
Yeah.
UCB. It doesn't matter.
Yeah, U dagger is like this. Or
You are actually writing U dagger BA.
Yeah, U dagger AB.
BA element.
Yeah.
BA.
So this
BA
is also
element
the
of
same
U.
as this. I've just written the two elements in a different order, but you can.
okay, so as UU dagger is identity matrix, it follows from that. Okay.
Yes.
Yes, absolutely.
Thank you, ma'am. Okay. Thank you. And also in the first part, while calculating the Coulomb integral for the when C is not equals to D, then it vanishes only. So that part made the wave function like you have written.
Yeah, so the integral where C not equal to D, that disappears because of the
Delta function.
delta condition. Yeah.
Okay, thank you, ma'am.
The same is hold for the. I just want to say the same is hold for the exchange integral. That is C and D become equal. But the reason this is exchange and that is Coulomb is only because of the appearance of the P12 operator. I think that is important to understand.
Okay.
Otherwise, structurally, both will be similar. D chi 2, chi C star 2, R1 to inverse, P12, chi C2. After the CD thing. But that is Coulomb and that is exchange because there is a permutation operator. So because of P12, actually in practice, what is following as chi C2 after D is equal to C will become chi C1 when the operator acts on a function. You understand? So that is why this is called exchange. So eventually this will not remain true. So the critical thing is the appearance of P12 operator. The CD equality is exactly same, coming from the unitary matrix. And that is the reason we say that the unitary matrix keeps the operator invariant, unitary transformation. I think that's the whole idea.
Okay, thank you, sir. But in one orbital case, you cannot differentiate between Coulomb and exchange.
What do you mean by that?
I mean, if there was some integral like some chi C2, suppose chi C1 to chi C2 2 and chi D1 to chi D2 2, then you can uh,
Yeah. No.
differentiate.
Yeah, but this is a definition of exchange operator. This operator is going to act on a function. When it acts on a function, automatically this will become 1, the other one will become 2.
Yes,
See,
the
that's the idea
appearance
of the P12 operator. Whatever is coming on the right of the P12 operator, it will interchange.
Okay. Thank you,
And
sir.
that interchange makes this operator different from the Coulomb operator.
Yeah, but in the from the angle of what we are trying to show here, it did not make a difference whether it
No.
was Coulomb or exchange. The
Yeah, this is
principle
just
is
C
the
and
same.
D. That's the unitary. But I'm saying that the basic reason this is exchange is what existed before. That the
Yeah,
appearance is given
exactly.
to operator. Yeah.
This thing, yeah. Yeah.
Okay.
That is the only thing that is different for the Coulomb and exchange. What we have done is exactly the same. So you should not have, if you understand the Coulomb, there should be no problem with the exchange.
Okay. Thank you, ma'am.
Yeah, yeah. So this is the thing. So now we see that the operator then, the Fock operator, with the transformed spin orbitals is the same as the Fock operator that we had originally. Okay. So now what else is present in the equation? So I will again write the equation that we had derived. So it looked like this. Okay. So we have seen that if we go over to a different chi prime, my Fock operator will not change. This will change. This will change. So the only remaining ingredient is the Lagrange multipliers. So will they change when I go over to a new set of spin orbitals? So to see that, will that change? So what we do is we project this equation with chi b, let's say, or chi. Okay, we have some b inside the Fock operator, so I'll call it chi c. So I have chi c, Fock operator chi a. This is equal to epsilon b a chi c chi b. Okay, and chi c chi b is delta cb from orthonormality. So this then reduces to epsilon. B becomes C. So epsilon C A. Okay. So what is epsilon prime A? AB or BA, let's say. Then what is it? This is from this relation that it is the expectation value of the Fock operator. We have, well, not expectation value, but like a matrix element of the Fock operator. Then epsilon BA is then chi B prime, Fock operator, chi A prime in the transformed case. Okay. Now what will that look like? Now, so this is dx1 chi b prime star, Fock operator. This is on 1, then you have chi a prime 1. And again, we have now, let's say, sum over C and D. dx1. So this will become chi star C 1 U C B star, same as before. Then you have F, and then you have chi D 1 U D A. And fine. Then we take out the u's again. And here they are all different. So it's not helping me. So I have this. I have u star cb. Then the rest of the integral, that looks like the expectation value of I shouldn't call it expectation value, matrix element of the Fock operator, chi c f chi d and u d a. And this is now then c d u c b star epsilon c d u d a. So here we could not simplify something. But from this element-wise relation, we can say that the matrix which contained all the which contains all the epsilon primes, let's say this is the matrix epsilon prime, is equal to U dagger, original matrix epsilon U. Okay, so the epsilon matrix is not invariant to the unitary transformation of orbitals. But that is a good thing because that is what we want. So what we wanted was epsilon prime to be diagonal. That is what we wanted. So now this tells us that we can now choose U such that epsilon prime is diagonal. Okay. So we identify U as the diagonalizing matrix of epsilon. Fine. This is clear. So then now what we do is we say that we have that the solutions of the Fock equation is some set of spin orbitals, and we want only those spin orbitals where epsilon prime is where the epsilon matrix is diagonal. What we have proven so far is that it is possible to have a set of spin orbitals for which epsilon prime is diagonal with a suitable choice of u. So the forward process would have been to solve the equation that we have obtained here and then find out the unitary matrix U, which gives me then a new set of spin orbitals and a diagonal epsilon. But you see, solving the equation in this form is difficult. So we do something something perfectly valid and much simpler. That is, we only solve for that set of spin orbitals, which gives me a diagonal epsilon matrix. Okay. So we directly solve for a particular set of spin orbitals for which epsilon prime is diagonal. And this is what we call the canonical Hearty-Fock equation. So this will only give me one particular set of spin orbitals. And now we can remove the primes in this equation. And henceforth we will use only the diagonal form of the, or the canonical form of the Hearty-Fock equation, which is this. Okay. This is the, and this gives me only a specific solution out of the variety of solutions that were possible from what we derived before. Okay. Now, other than this solution, where epsilon is diagonal, which is equivalent to saying that the matrix chi A F chi B, this is also diagonal, and this is called, then, so if I say that the matrix element of F between A and B is FAB, then the matrix F is called the Fock matrix. Okay. Then the Fock matrix is also diagonal. That's just a way of saying the same thing, okay? Epsilon matrix or Fock matrix. So which means that every spin orbital is now associated with only one Lagrangian multiplier, which has the dimensions of energy, and that is called the energy of the spin orbital. Fine. Okay. So this is the most common and most widely used equation, the canonical Hartree-Fock equation, which gives me a diagonal Fock matrix. Alternatively, you could have wanted some other set of spin orbitals. So some other conditions for obtaining a particular set of spin orbitals you can want something that is most localized. So what do I mean by most localized? I mean that they have the smallest spread, the smallest spatial spread. And then that they would be called localized orbitals. So you can find a suitable condition and you can use that to obtain another Hartree-Fock equation, which is not canonical, that is something else, and then my Fock matrix will again not be diagonal. Okay, but this will be a different condition. Or sometimes you obtain the canonical solution and then you explicitly apply a unitary transformation to satisfy some condition like localization. You can do that. You can also have something that diagonalizes some other matrix. So you can want some maybe property matrix to be diagonal. Now what use that would serve is of course up to what you want, but it is always possible. Okay, so you find some set of orbitals which satisfies conditions that you want it to satisfy. So this condition is the second most common, especially for visualization. I am bad at this. Okay. Visualization of chemical bonds, because chemical bonds are intrinsically local as we think about it, and if you have very delocalized molecular orbitals, then visualizing them is of no use because you can't identify where the bonds are. So this is the second most common thing that is done. If you have a theory with more complicated structure equation, then sometimes you might want some other quantity to be diagonal, not the energy of the orbital, but something else. So maybe the energy is not important to you. That is also possible. Some other matrix, maybe some density matrix, okay, or property, something else. Okay. But those are much less common. Okay. We will in this course at least we will deal with the canonical Hartree-Fock equation only. Okay, so we will stop the teaching here for today, but I want you to solve an exercise. Okay, so let's do exercise 3.3 of Zabostron, if you'll have that in hand, otherwise I will. .3 of Zabostron. So this is something we partly derived last time.
Assignment.
Yeah, I didn't hear. No, not assignment. You do it now. So we partly did the derivation last class, but I want you to complete it. I will take out the book 1 second. This is a bit long in writing, but actually it's simple. So did you manage to find the pairs of terms which are complex conjugates of each other?
Yes, ma'am.
Yeah. So you got the expression that you're supposed to get?
Yes, ma'am. Almost I have got the answer.
Almost? Okay.
Yes.
Is anyone stuck who doesn't know how to get the terms? Just tell me, because I cannot see anyone. Like if you were in class, I would have been able to see who is just sitting and thinking. But now you have to tell me that you don't know what to do. There's no problem. I can give you a hint.
I am a bit confused regarding which terms will be equal. Means to cancel out this
Okay.
half factor.
Okay. So in the Mulliken form, when you think of the integral form of it, then you have so from the four indices, you have the first two indices belonging to electron 1, the second two belonging to electron 2, and in each pair the first orbital is starred and the second is not. Okay, so if you just interchange electron 1 and 2, you're always allowed to do that. Those integrals are equal, so you can so the first two indices can be interchanged as a whole with the third and fourth. So that is
Yes,
one
then
method you will need to use.
then
And
like
the other
first and
thing,
third term.
so first and third term, yes, they are equal since you also have a sum over A and B. So that is the second thing you need to do. You need to note that you have a sum over A and B, and you can, so if you put the summation now in front of every term, you can replace the A's with B's and nothing would change. So using these two facts, you can show the equality. Yeah, so first and third are equal once you interchange A and B. Let's say in the third one. So basically there are two kinds of terms. One where the delta is on a starred orbital and one where it is on an unstarred orbital. So those are the only two different types of integral. The others will be equal by some, like they will fall into these two groups, every integral. And in the exercise, the terms they have written are the ones where the delta is on the starred orbital. And in the complex conjugate, then you will have the deltas on the unstarred orbital. That is all. Fine. So how many are done? Just tell me.
Ma'am, I find that, and uh, I have this one question that you just I have asked earlier, that A and B are just dummy variables, so interchanging them will be equal only after taking their sum, right? Otherwise not.
Yes, the total sum is independent of interchanging A and B. Yeah. So you have to repeat the summation sign in front of every integral before you interchange A and B.
Yes, the complex conjugate part I have done.
Okay. So before you interchange A and B, you have to repeat the summation sign. So I hope, so all of you get my point? No? So then let's go back to chapter 2. And the next exercise that you try is exercise 2.2. Maybe have any of you already done it? Exercise 2.2 is show that the Hearty product is an eigenfunction of the Hamiltonian sum I 1 to n small h I with an eigenvalue E, which is a sum of all the orbital energies. Exercise 2.2.
It is very basic principle, I think.
Yes, very basic.
Uh,
Only like maybe 2 lines.
yes, ma'am.
Yeah. So you just need to apply the eigenvalue equation.
What is the page number?
This is page 48 in my PDF. Well, it's at page 48 of the print and page 63 in my PDF.
Actually, this is same as the non-interacting theorem that was taught to them.
Yes.
The non-interacting Hamiltonian theorem that we taught. It's exactly the same. The
It's
same proof.
exactly the same.
Yeah, except that now the anti-symmetrization is not there. That's all. Since you're talking about Hearty product, I think.
Yeah. Can everyone see it? I actually want to know if someone doesn't see it. If everyone sees it, then absolutely fine. It's okay?
Madam, can you repeat the question number?
Exercise 2.2.
2.2.
When you study from Zabostun, try and do every exercise. I am trying as possible in these tutorial classes, but of course we can't do all of them. So those who have already done 2.2, you can go on to 2.22, which is a little bit more thinking, but still 2 lines. 22, 2.22. This is page 87 of the actual book.
Now here what they mean by E up down?
Uh, E up down means they have given you to solve alpha 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 beta beta matrix element. So up down means alpha beta matrix element. So every wave function has 2 electrons. So did you understand?
No, I mean E up down means I have to find the energy of 2 electrons of orbital.
No. So when they say psi up down Hearty product, so it's C psi 1 alpha, psi 2 beta. And that is
Oh,
the,
acha.
yeah. And E up down means the expectation value of psi up down, psi up down. So bra
Okay.
is also psi up down, het is also psi up down. So you have to find 2 expectations values basically for the 2 wave functions that are given and show them to be equal. So done. So everyone has done 2.2 and now also 2.22.
Yes, ma'am, done.
Done. Okay. It is simple enough, right? No problem. Okay. So now we will talk a little bit about the Fock operator. So can someone tell me if the Fock operator is Hermitian or not? Can anyone guess? So let's say, so when I say a Fock operator is Hermitian or not, you can consider it. So you can consider the matrix of the operator and say if that matrix is Hermitian or not, and check that if the matrix is Hermitian or not. So what do you think? Is it or is it not Hermitian?
Yes, Fock matrix is diagonal matrix.
After you, the Fock matrix is diagonal after you solve it.
Okay.
Yes. So it is. So then it is Hermitian. Yes, if it's diagonal, it's definitely Hermitian. And if it is between any two functions, let's say these spin orbitals are not yet solutions to the canonical Hearty form. They are any spin orbitals. So the Fock matrix is diagonal only when the spin orbitals are solutions to the canonical Hartree-Fock equation. But for any two, generally any two spin orbitals, then it is not diagonal, but is it Hermitian?
Ma'am, it will be not because EK part is K part is not Hermitian.
Ka part is no, Ka part is also Hermitian.
I think it will be Hermitian because all three parts are Hermitian by itself.
Yeah, exactly. All three are Hermitian. So to do transpose and conjugate, what you are basically doing is you're interchanging the AB and you're taking complex conjugate. So when you do that, then even the exchange integral part is Hermitian. So all three parts are Hermitian and the Fock matrix is also Hermitian, which also ensures that the eigenvalues are real. So your orbital energies will always be real. So it is important that the Fock matrix is Hermitian. Because if you get a complex energy, that doesn't mean anything, right? Then it would have been difficult to identify the epsilons as orbital energies. They would have been something else. They would not have been energies also. Like a complex energy is not good. So it's Hermitian. Fine. And okay. So in the last 15 minutes, should I start something or not? I think I will just let you go today. But okay, before you go, just tell me one thing. Do you all have access to some sort of compute, like a common computing facility? Like, do you all have accounts in some computer?
Computer means?
I mean, say if I wanted you to run a code, I will give you the code. Do you have access to some computer
We
to
have
run it?
Python programming in my laptop. I have Python language.
But in your laptop, you don't have
Yes.
access to like an institute computer somewhere that you can
No,
log into.
no, my own laptop.
Okay, okay. I have access. Okay, I will find out. So I was thinking that maybe once we complete Hearty fork, you can actually run a Hearty fork computation. That would be nice. So then I can install the software on a common computer and see if all of you can get access to it. So for any other course, have you ever done any sort of computational thing on a computer?
No, not an institute computer.
Okay, but on your own computers you have done.
Yes, common laptops.
Okay, and all of you have laptops. I hope. I mean, or a desktop. Do you know if someone is doing it from a phone? I see that not everyone is here. But I think I will try and do a common computer.
Or you
You would
can
be
just
interested,
present
right?
us the program. Like,
I can no actually I would prefer that I install it on some common platform and all of you use it to run it.
okay.
Yeah, I prefer to do that. But if it doesn't work, then I will give you all the link to the program and you all can all try it. But that's like waste of effort for you. All of you will try and install the same thing. Right.
Okay, okay.
So I will, okay, I'll find out. Okay, fine. So we can finish here today actually. And next class we will finish the Hearty fork hopefully.
Madam, can you repeat the why KB and JB are Hermitian?
Why
I mean the
KB and JB? Okay, so if you look at the operator form, that is probably
exchange and the Coulomb.
exchange and Coulomb. Yeah. No, I'm thinking if it is easier to look at the operator, if you want, it's easier to look at the integral. I think it's easier to look at the integral. So if you look at JAB, then if you interchange AB and take a complex conjugate, you get the same integral. So only your 1 and 2 are interchanged, but that doesn't make a difference to the value of the integral.
Okay, ma'am. Thank you.
Yeah. Okay. Any more questions? You can also ask me questions as and when you are studying it. So on WhatsApp or something. No problem. Or you can wait for the class as you wish. Okay. So we will finish now. Someone stop the recording. Thank you. Bye-bye.